Texas A&M University.
I really needed one of these. I had one confiscated from at airport
seriously?
security. Yeah, it was in Ireland, but yeah, the U.S. they don't mind, but in Europe they do. Well, thank you very much for that gracious introduction. Can everybody hear me okay in here? Okay, that's great. And I've had a really great day touring the labs here and talking with people. So I much appreciate the invite to come visit Texas A&M. The work I'm going to tell you about is our latest work in a technique that Alexei mentioned on high-order harmonic generation. But what this technique lets us do is generate coherent X-rays on a tabletop using tabletop scale femtosecond lasers. It's essentially realizing the dream that I had as a graduate student when I was doing my PhD work, that we really should try to make a tabletop X-ray laser. And we don't use the lasing process directly here to make X-rays, but rather we take a short pulse of light from an infrared laser and upconvert it into the X-ray region of the spectrum. The effect is the same, though, that we can generate coherent light in a tabletop scale at wavelengths as short as less than a nanometer wavelength at this point. We don't know how far we can go in terms of how short of a wavelength of coherent light we can generate. But we've recently made a very large step forward, and actually it's opened up a whole new area of investigation. This work is done in the group that's run by myself and Margaret Renan, and we're in GILA, which is an institute on campus at the University of Colorado. It's an institute that's joint between the university and the National Institute of Standards and Technology. And this is a somewhat dated picture from our group, but we have Margaret and I run a joint research group with about 25 people or so. We're also part of an engineering research center funded by the NSF. That's 3 groups. Our group, Jorge Roca at Colorado State, and a group at UC Berkeley. And it's in this context that this work is done, and also with a number of different collaborators. And the work I'll tell you about was actually primarily the thesis work of 2 students, Tanya Pontminchev and Ming-Tang Chen. They're both still with us as postdocs, although Ming-Tang is moving to a faculty position in Taiwan soon. And a number of other students have contributed to this work. And also in terms of theory, we've worked with Andreas Becker and Agnieszka Jaron Becker, who are also at GILA. But also very important part of this work was done in collaboration with Andreas Baltuska at the Technical University of Vienna. There are people here at A&M who also collaborate with him. So he's a great guy to work with. And also on theory, we've done work with a group at Salamanca and a group in Cornell. So just a brief outline of what I'll tell you about. The main part of my talk is going to be recent work on developing this tabletop X-ray laser light source. And to make coherent X-rays on a tabletop, we're using the technique of nonlinear optics, which many of you study here, but we're taking it to the extreme, where we're taking light from an infrared laser and combining coherently combining up to 5,000 photons from the laser to create each X-ray photon that's emitted. The light also comes out in a very broad bandwidth, and this actually gives us the potential in the future to access shorter and shorter time scales because energy and time are related by the Heisenberg uncertainty principle. And we're actually approaching the ability to access zeptosecond time scales. The zeptosecond is 10 to the minus 21 seconds. And we're not there yet or anywhere close to it, but clearly the potential is opened up for doing that now. And also, to the extent that I have time, I'll tell you a little bit about work that we've been using, taking these tabletop X-ray laser sources and using them as a tool for science. And we've done a number of different experiments in looking at materials, properties, and dynamics in materials with very short pulses of X-ray light from these sources. And also, we can use the coherent light to image with very high resolution. And these topics are of increasing interest to industry because nanotechnology is happening. It's in our iPhones these days. Transistors keep getting denser and denser and smaller, and industry needs new tools to look at what they're doing, and these sources are useful for that. So just to set up this talk, I'll first just make the point that the laser itself has really transformed science, technology, and society overall. We wouldn't have the internet or our iPhones or any of our other gadgets if we hadn't invented the laser. The laser gives us coherent light that is essentially energy in its purest and most controlled form, where we're controlling all of the characteristics of that energy, and that it can propagate at the speed of light. We use lasers routinely in optical communications and in technologies like laser surgery, remote sensing, military applications, optical storage. And so it's really been a transformative technology. And that's what the goal of our work has been, is that X-ray light also transformed our world. So X-rays have been around for a little more than a century now. Well, Wilhelm Röntgen invented the X-ray tube in 1895. And what that X-ray tube consists of is it's essentially a vacuum tube where you boil electrons from a filament, accelerate them in an electric field, and slam them into a target at high energy. And that high energy, very rapid deceleration of these electrons generates these very high energy photons that are useful for everything from airport security to medical imaging and advanced techniques like tomography, but also for very basic science applications, like, for example, the helix structure of DNA was discovered through X-ray diffraction. So X-rays are great, lasers are great, but the X-ray tube on which these advances have been based is basically just an X-ray light bulb. It's incoherent X-ray light, not coherent X-ray light. And if you could make coherent X-rays, that opens up a whole new realm of possibility. And there has been some progress in this. So, for example, this little movie in the corner here is an X-ray, soft X-ray tomography picture of a single cell that was taken with X-rays from a synchrotron light source. X-rays are short wavelength light, and the wavelength and the time, the spatial scale and the temporal scale for processes are linked together so that X-rays are light with very short wavelength. They're ideal probes of the nanoworld. You can image very small features see individual atomic species, either directly or also through characteristic X-ray absorption edges. And also, as you go to smaller spatial scales, dynamics happens faster and faster, so that at very small scales with X-rays, you have the potential to do stop-motion pictures of, for example, a chemical reaction. So the potential there, if you had coherent X-rays, very well-controlled pulses of light at short wavelength, is quite large, and that's motivated the development of very large-scale light source facilities. And this is an example of a synchrotron light facility. This is the facility at Lawrence Berkeley Lab. It's a big synchrotron ring that they put electrons through, and as the electrons circulate through this ring, they generate X-rays as they're accelerated, and those X-rays are used in a variety of experimental applications at the synchrotron light source, including spectral microscopy, photoemission, material science, atomic and molecular physics. So we do have access to X-rays through these synchrotron facilities. They're not fully coherent coming from a synchrotron, but they're partially coherent and very bright, and have proven to be very useful. But one real disadvantage is that this is a large-scale facility. So this is the advanced light source. I don't know if there are any people in here, but there are cars down there for size perspective. It's a $200 million facility, and this is a fairly modest scale for these light sources. So it'd be nice to have something more convenient. For example, one thing that you couldn't do yet is use those X-ray tomography pictures of a single cell. You couldn't use that in a clinical application right now because you can't have a synchrotron at every hospital to generate the light to make the images. So we'd like to figure out how to make coherent X-rays on a tabletop. The first thing that might occur is, why not just make an X-ray laser? The laser is based on a process of stimulated emission of radiation, and the basic physics of that process was outlined first by Albert Einstein in the 1920s. And one of the things that he derived was this ratio of spontaneous emission to stimulated emission, which basically tells you that if you want to make a laser, you need to get gain for optical gain for light, and the cost of that is rising very, very rapidly as you try to make optical gain at much shorter wavelengths. So if you take Einstein's basic expressions and derive a power scaling for how much power you need to make a laser at a given photon energy h nu, it goes as roughly the 5th power of the laser wavelength. And what that means is that, you know, I can make a laser pointer that's powered by a couple AA batteries. That's at a wavelength of nominally a micron. So a laser at a micron, let's just say you could make that with a milliwatt of laser energy. Now apply this 5th power scaling and go from the near infrared through the visible, through the ultraviolet, and X-ray wavelengths. And what you see is, if you could make a laser with a milliwatt at a micron at 1 nanometer wavelength, which is soft X-rays, that would... What? This is, you mean, how did I get that 5th power scaling?
Normally we know what is the power per unit area.
Yeah, there are a lot of variables in making a laser. This is basically, if I need, the base requirement for making a laser is you have to get optical gain to overcome losses in a resonator. So this is just calculating how much power you need to make a fixed amount of optical gain. The cross-sectional area would affect how much power you can get out of the laser. But I'm just saying, to make it work at all, the base power scaling is roughly as the fifth power. So, you know, a milliwatt goes to a terawatt at 1 nanometers, and at 1 angstroms, that would be a petawatt peak power. And in fact, these numbers are somewhat conservative compared with what you really need to make a true X-ray laser. The power requirements go up very rapidly. It makes it seem at first glance that, well, an X-ray laser just will not be a tabletop scale apparatus. And in fact, the first experiments in making X-ray lasers originated with the Star Wars program in the 1980s. And in that program, Edward Teller proposed to Ronald Reagan to power X-ray lasers with nuclear weapons. And the idea was sort of given in this picture here. You'd have weapons that where you'd explode a nuclear bomb in space that would power an X-ray laser that could then shoot down a missile. And now this concept has always been, was dubious at the time. It's still dubious, but the reason they proposed it, really, if you look at it, is that these guys wanted to make an X-ray laser, and they looked at the scaling and decided this is the way to do it. Obviously, this approach has its disadvantages, right? Especially if you want something on a tabletop. I don't want that on my tabletop, right? So you have to think about another way of doing this. Now, more recently, X-ray free electron lasers have been developed, and the first and most successful of those is the LCOS, the Linnet Coherent Light Source, which is an X-ray free electron laser that was developed at SLAC. And this is a picture of it, and you might not quite understand what you're looking at here, but this is the freeway interchange outside of Stanford. What they did to make an X-ray laser here is they took the SLAC 2-mile-long linear collider, took a very high-energy electron beam, and by sending it through a very long, very precise undulator configuration, they could make coherent X-ray light with this device. Now, this is definitely a step up in usability compared with that, but it's still a very large-scale facility. It's about $1 billion, and you know, obviously, you need aerial photographs to capture the scale of it. Our goal is to do better than that and to make something that really could be used as a laboratory tool, and in fact is being used as a laboratory tool. And the way we do that is to use a process called nonlinear optics. Nonlinear optics actually just went through its 50-year anniversary, and this is a picture of the first experiment in nonlinear optics that was done by Peter Franken at the University of Michigan. And what he did was he took a ruby laser, which was the first type of laser that had been invented, and only invented the year before that, focused the light with a lens into a quartz crystal, and by separating the light that emerged from that quartz crystal with the prism, what he saw is that most of the light just came through the quartz and, you know, was the same color it was coming in. But a small fraction of that light was frequency doubled, meaning that in the quartz crystal, photons from the driving laser were coherently combined together to make a coherent beam of light where the photons had twice the energy, or half the light had half the wavelength. So converted, in this case, red light into the ultraviolet through a process called second harmonic generation. Now, the physical origin of this second harmonic generation process is simply that in a material like quartz, the electrons, it consists of electrons and ion cores. The electrons are bound inside a structured lattice. And in some cases, in these lattices, if you push on the electric field corresponding to that laser light pushes on the electrons in the material, and in some cases, the response of those electrons is not linear. In other words, this diagram tries to illustrate that if you have an electric field and you look at the polarization of an atom in this material, you might find that the electric field pushes in one direction, the polarization responds differently than if the electric field is in the other direction. The net result here is that the electrons in the material oscillate nonlinearly, and if you think about that in terms of Fourier transform relationships, that nonlinear motion consists in frequency space of higher order harmonics. And one way of thinking of this is like taking your electric guitar and turning the volume up to 11. The acoustic waves that are the signal going through your amplifier gets highly distorted, and the result is a screechiness that corresponds to these higher order harmonics. Now, in that first experiment, an interesting sidebar is the fact that if you actually go to the PhysRev letter paper that outlined these results and you look at the experimental data, they took it on a photographic plate. This spot here is oversaturated, and that's where the laser spot hit. This arrow here points at the spot that corresponds to the second harmonic light that was generated. You notice there's nothing below that arrow there, and that's because the typesetter thought that it was a dust speck and whited it out before it got published. So the experimental data wasn't there. But so now what we're going to do is fast forward. About 25 years was the first time high harmonic generation was discovered. And the high harmonic generation process looks pretty much the same. We take a pulse of light, focus it into a gas, and what we see is that we can in fact take a small number of these photons from the incident laser and upconvert them not to the second harmonic, but to the, in this case, it was like the 13th, 15th, and 17th harmonic is what we're seeing. And the way that the difference here is mainly that we've just made the laser pulse a whole lot shorter. So now we're using a femtosecond laser pulse. This pulse here is actually a fairly good representation of what a femtosecond light pulse would look like if you could stop it at one instant in time. It's only a few optical cycles in duration, and because the light pulse itself is approaching the fundamental limit of how short you can make a light pulse, that also allows you to crank up the intensity in your experiment much, much higher, because you don't need a whole lot of energy to make a very intense light pulse. When this light pulse interacts with the gas, what we now understand is the origin of those high harmonics is that the electric field of the laser can field ionize an atom, literally pull an electron out of the atom. Then the electron starts to accelerate in the laser field, but the laser field is oscillating, so the electron motion will also oscillate. Some of those electrons will emerge from the atom through a tunnel ionization process, start to oscillate, come back into the vicinity of the atom from which they came, and if they recombine back into the ground state, those electrons are abruptly stopped, and they have to give up their kinetic energy, and they give that up as a high energy X-ray. So this is the idea. Electron wave function bound to an atom. An applied laser field at one instant in time looks like it's basically suppressing the Coulomb barrier, and then the electron can tunnel out of the atom. Then, at some later point in time, the electron gets driven back into the vicinity of the ion and generates this X-ray. And if you think about this process, certainly this isn't how people came up with the high harmonic generation process. It was a discovery. But if you think about it after the fact, in fact, what you're doing is you're making a coherent version of this X-ray tube. Here, in its standard Rankine X-ray tube, the electron collisions that generate the X-rays are purely random. If you want to make that X-ray like coherent, what you have to do is you have to make that collision coherent. And think about how you might do that. Well, electrons are have a wave nature, so they have a coherence to them. Maybe you start with an electron in a coherent state, well, the ground state of an atom. Then what you need to do is you need to accelerate that electron in a very coherent manner, apply a strong electric field, and tunnel ionize from the ground state of an atom. Okay, now you have an electron that's accelerating very rapidly. Well, the next thing it has to do is collide with a target, but that target also has to be coherent with the electron. And the only way you can do that is you bring the electron out, then switch the sign of the electric field and accelerate that electron back to the same atom where it came from. Now, that electron is slamming into a target that is actually part of the same electron wave function from which the electron originated. So every part of that process is now coherent. And the result is that the X-ray radiation that you generate is also coherent. It is also fully consistent with the second harmonic generation process. It's just a nonlinear response of the electrons in the material to an applied light field. But it's really quite an elegant process. And in fact, from this simple picture, you can calculate things like, for example, what the spectrum of the emission should look like. What it turns out is that each one of these spectral peaks corresponds to an odd number of photons coherently summed together. You can't do an even number of photons in most circumstances because you need a so-called inversion asymmetry. And we're doing this in a gas, so there is no asymmetry. But you get the fundamental, the third harmonic, the fifth, the seventh, the ninth, and so on, up to a cutoff photon energy that actually relates directly to the kinetic energy of the electron at the time when it undergoes this so-called recollision process. And you can do a combination of tunneling physics and classical trajectories to predict that relationship. It turns out that that cutoff wavelength is proportionate to the intensity of the laser used to do the ionization, and also to the square of the wavelength. And this part, the square of the wavelength, is one thing that's really intriguing, because if you think about it, this means wavelength and photon energy are related by inverse, right? So this would mean 1 over h nu squared would be one way of writing it. Now, instead of having a power requirement to make these X-rays that goes as the fifth power of the photon energy, it's actually the inverse square power. It's certainly not that simple, but that's the basis for why this is such a useful process. It's because you've totally circumvented the very unfavorable scaling that you used to have. And now you have something that looks a lot more interesting. That wavelength is the wavelength of the laser that drives the process, not the wavelength that you're generating. Yeah. Yes, of the femtosecond laser. Let's see. Yeah, this is the laser wavelength, and this is the wavelength that you can generate. Yeah, so they're inverse to each other. Very interesting, and we'll come back to that. You can certainly do the quantum mechanics of this process, and in fact, semi-analytical or semi-classical quantum description of this process was developed in the mid-1990s, and this is an example of how that works. Essentially, you end up with predicting a dipole response of an atom where individual terms correspond to tunnel ionization of the atom, propagation of this electron wave function in free space in its oscillation trajectory, and then recombination. And this is some pictures developed from computer simulations of what that electron wave function looks like at different instants in time. The atomic core is at the center here. Most of this is free electron wave function. So we can generate these short wavelength photons. They're coherent with the driving laser field, but the other big issue with this process is to phase match the high harmonic generation process. And this view graph illustrates what phase matching means. Essentially, you're taking a femtosecond laser, passing it through a gas of atoms here, and generating this EUV light. But there are a large number of atoms here distributed over a large volume. And what you have to make sure of is that when one atom emits X-ray light and that light starts to propagate, it adds constructively with the light that's emitted by other atoms farther down in its propagation. That's what phase matching is called. Here, in this animation, we're not phase matched. The idea is the driving laser field propagates this way. We generate a photon from this atom, one from that atom. But if you look out in the far field here, you notice the phase of this electromagnetic field is different in the two. And the reason for that is because the speed of propagation of these two waves is not necessarily the same. If it were vacuum, they would be all traveling at c, but we're not in a vacuum. Phase matching corresponds to when all of the waves travel at the same phase velocity. All of the emission adds constructively in the forward direction. And in that case, what you find is that the intensity of the harmonic field scales as the square of the propagation distance, because the electric field keeps adding linearly, and intensity is proportionate to electric field squared. Now, in nonlinear optics, phase matching was the critical enabler. An example of that is this laser pointer. Green laser pointers are actually infrared lasers that have a frequency doubling crystal in them that takes the infrared light and combines infrared photons together to generate green light. This is powered by a battery, and the green light that's generated from it is quite bright. That's because people figured out how to phase match the second harmonic generation process. They do it in these laser pointers by using the birefringence of a crystal to arrange for the speed of light at two very different wavelengths to still coincide with each other. So that's what we have to do for the high harmonic generation process. And at first glance, that sounds really difficult, because now instead of just having infrared and green light, we have infrared light and X-rays. How do you get them to travel at the same speed through a medium? And things were stuck in this field for quite a while, but it turns out that phase matching for high-order harmonic generation works, and it works in a very natural way. The idea is that the best way to do this is take your laser light and focus it into a hollow glass tube. That tube acts as a waveguide and gives a very nice uniform intensity of the light over a long propagation distance. Then it turns out that the speed of light in this waveguide is determined by a number of different factors. Propagation in the waveguide alters the speed of the light. The index of refraction of the neutral gas that has to be in there actually slows down the light. And since you're generating these X-rays during the course of ionization of the gas, you're going to have a free electron plasma there also. It turns out that the index of refraction of a free electron plasma is actually slightly less than 1. The index of refraction of the neutral gas is greater than 1, and you're ionizing this thing. It turns out that the base idea here is that you balance the ionization and the index of refraction of the gas, and at some point during the core time evolution of this thing, where you're ionizing the gas, it turns out the index of refraction of the gas to the laser light is going from slightly greater than 1 to a number slightly less than 1. When it passes through 1, that means that the phase velocity of that pulse is the speed of light. The X-rays that you generate are generally don't see the gas nearly as strongly because their energy is well above the resonant absorption. So they're traveling at about the speed of light. So what it turns out in this process is that phase matching happens, and it happens at a certain time within the laser pulse when the level of ionization is appropriate. What happens then is that you then get, that's when you generate the phase matched emission, and most of what you see coming out of the gas is actually generated during a short time window when that phase matching is optimum. And that's something that people didn't understand at first. But it also introduces a limit, which means that you can't just generate higher energy X-rays by turning up the intensity of the laser. If you turn up the intensity of the laser, you just ionize sooner. And if you ionize sooner, you'll mess up the phase matching of the process because you get too much plasma. So the presence of too much plasma speeds the laser up too much, and then you get no phase matching of the process. And this defines a critical ionization level above which phase matching is impossible. And this is the limit to what energy photons you can generate from this process. It's not the single atom physics. It's the phase matching of the process that limits the photon energies. And for the last 10 or 15 years, most of the work done in this field has used tri-sapphire lasers operating about 800 nanometer wavelength. It turns out for that the limit for the coherent upconversion process is a photon energy of about 150 electron volts. That's in a region of the spectrum called extreme ultraviolet. It's interesting, for example, the next generation photolithography for super advanced microcircuits will be done with light in the extreme ultraviolet region of the spectrum. But you'd still like to figure out how to get beyond this limitation. And that's what we have done recently. And it turns out that the best solution seems to be a fairly simple solution to this problem. And that is, if you go back to this relationship for how the energy of the X-rays corresponds to the characteristics of the laser driving the process, the X-ray energy is proportionate to the intensity of the laser, and that's the knob everybody was playing with. Let's just turn up the intensity of the laser. But there's also this second one, the wavelength of the laser squared. Well, you would think this has a squared in it, so why didn't we think about playing with that knob first rather than the intensity? And the fact is most lasers have an intensity knob. Most lasers do not have a knob that you can simply turn to tune the wavelength. Some of them you can do a little bit of that, but in general, intensity is always the easy variable to change. It turns out in this process, tuning the wavelength is very useful. And I'll try and illustrate how we now understand how to optimize the high harmonic generation process, because I know there were some questions about this today. Think about a short light pulse incident on a gas to generate high harmonics, and I'll take argon gas in this case. 0.8 microns is Ti-sapphire laser, and I'll take a pulse duration of 8 cycles, full width half max. That's about a 25 femtosecond pulse. What you want to do to generate as harmonics as efficiently as possible is adjust the peak intensity of this laser so that just at the peak of time of the pulse, the fraction of ionization of the gas is at this level that achieves phase-matched conversion. That way you're generating the highest energy photons in the optimum condition for maximum conversion efficiency. In this case, it's about a 4% ionized argon gas. So you adjust the intensity of this pulse to hit critical ionization at the peak of the pulse, and then you can predict the photon energy that you get. And it turns out that under these conditions, you generate light up to about 50 eV photon energy. This is a fairly simple, almost an analytic calculation, and it fits the experiment remarkably well. But that's what we're going to define as the so-called phase matching cutoff. Now let's do it for a longer wavelength laser, like 1.3 microns. I'll keep the same duration in terms of number of cycles. It turns out that phase matching here happens at a slightly lower percent ionization of the gas. But then if you look at the X-ray energies that would be generated at that peak intensity, turns out that the lambda squared term wins out here, and you're now generating photons optimally at about 100 electron volt photon energy. So you turned up the wavelength of the drive laser by a little less than a factor of 2, and you gained about a factor of 2 in the photon energy. So the efficiency is another question, and I will get to that. But so hold your question for a couple of your graphs. It turns out that this basic scaling that I went through, you can actually put all the pieces together. This includes tunnel ionization probability and this classical trajectory calculation and a bunch of other things. You can actually get an expression for what photon energy you should be able to get for given conditions. Developing this expression really took 15 years, and most of it, not 15 years of somebody staring at a piece of paper, but 15 years to really understand that you could do something like this. And it was really a matter of understanding nonlinear optics in a regime that not only is non-perturbative, meaning perturbation theory can't describe the harmonic generation process, but also that it's time dependent. The phase matching conditions are changing on a femtosecond by femtosecond time scale. And we really didn't understand how to think about that problem until recently. And now I think we've kind of figured it out. TAMU Potmanchev was instrumental in this, and this expression is actually in a recent Science article that we did. If you plot this expression, so this is drive laser wavelength on the x-axis of photon energy that you phase match to on the y-axis, what you find is it's pretty favorable. If you remember our single atom cutoff, which is just the physics of this oscillating electron, gave us an expression proportionate to lambda squared and the intensity of the laser. Including phase matching in here, we get a proportionality of about lambda to the 1.7. So almost as good, not quite a square dependence, but certainly we can run with this. And the first question is, of course, is this going to work in the lab? One thing, and this addresses the efficiency issue, is that people in the mid-2000s, people had started to think about doing high-order harmonic generation with mid-infrared lasers, and it was easy to convince yourself that it wasn't all that promising of a prospect. And the reason is this, that the other thing that happens when you use a longer wavelength laser is that the electron trajectory gets longer and longer. So a short wavelength laser, the electrons are oscillating really quick. They don't make a big excursion before they come back. A long wavelength, the electron comes way out and then comes back. And of course, the electron wave function is spreading in the transverse dimension also. So the question is, how much of that electron wave function is actually going to interact when it comes back? These pictures are quantum simulations that try to get at that. But what people had determined was that spreading of this quantum wave packet meant that the yield from a single atom scaled in a very punishing way as the laser wavelength to the minus 5.5 power. People looked at this, they did a few experiments that seemed consistent with it, and then thought, high harmonic generation is going to be fundamentally limited because on the one hand, if you use short wavelengths, you can't phase match to high energies. If you use long wavelengths, you just don't generate much light. This, it turns out, is an incomplete picture. You really have to look at all of the nonlinear optics of this process. And one thing that it turns out happens is as you're using a longer wavelength laser, you're generating light at shorter wavelengths. The light at shorter wavelengths is actually going into regions that the atoms are much more transparent to. So the medium gets more and more transparent at higher energies, and that means that you can pack more atoms together. So the result, if you take all that into account, is this is a little bit of a complicated 3D graph, but basically if you look at this line here, which is the predicted conversion efficiency scaling for high harmonic generation in helium as a function of wavelength of the laser, you notice that this line isn't going down, it's actually going up. What's happening here is that you can use much, much higher pressures of gas in your interaction region to generate the high harmonics. And because this is a nonlinear process where the electric field scales constructively, you can make up for that very punishing single atom scaling. The other thing it turns out is that helium is the best medium, generally speaking. There may be some particular exceptions, but generally speaking, helium is a really good medium for making high harmonics out of. That was exactly counter to what any experimentalist would have told you in this field. They all put helium gas in their apparatus and saw no photons coming out and dismissed it as it's not worthwhile. So you want to see if this works in the lab, and I know I'm starting to run out of time here, so I'm going to go through this really quickly. These are the theoretical predictions that TAMU made. The dots are the experimental data showing that as you scale the wavelength of the drive laser to longer wavelengths or lower photon energies, that center of the emission and the cutoff, the highest energy photons that you see, move to shorter and shorter wavelengths. Really interesting. This is one of these cases where physics is really working for you instead of against you. And those are rare, we all know. These are data for helium gas. And we used a 0.8 micron, 1.3 micron, and 2 micron laser here. What we see is, again, we follow this scaling quite nicely. Now we're generating light at most efficiently at about 500 eV. This is actually the wavelength range that's of interest for this bioimaging that I showed you at the beginning. So we now know how to do that. We know how to make coherent light in the wavelength range of interest for biological imaging. The other thing I'll point out in this data is that in these plots, the y-axis here, the x-axis is a photon energy, and here you see individual harmonic orders. Here you don't, because those peaks are getting closer and closer together because the drive laser wavelength is smaller. But the actual interaction pressures that you need to use to optimize the process are going very, very high. This is a very different regime than anybody has played with before for this process. Now, the usual high harmonic experiment was you puff a few torr of gas into a vacuum chamber, and you go through that and you generate some VUV light. Now we're using pressures of more than 10 atmospheres that the laser is propagating through. Not clear that the laser pulse should stay together propagating through a high pressure gas like this, but it turns out it does quite well. And finally, to give this a test at a much longer wavelength, we went to Andreas Baltuska's lab in Vienna, where they had just developed, actually we participated in development of this laser at 3.9 microns. So this is a bright femtosecond laser pulse at 3.9 micron wavelength, going into a hollow glass tube filled with about 40 atmospheres of helium gas. And what we see coming out here is X-rays with a spectrum that spans all the way up to 1.5 kiloelectron volts. This is a picture of the beam. There's a significant number of photons there, enough that we understand that with better lasers, this will be a very useful light source. The conversion efficiency is still nowhere near what we get with a laser pointer, though, because it is very high order conversion into a gas that still is absorbing. So it's about a 10 to the minus 7 is our best guess for conversion efficiency. But, it works very nicely, and we can just verify that these are real X-rays and not an experimental artifact by putting different materials in the beam and seeing the absorption edges. This is a little more on the laser that was used to do this. It's based on a principle called optical parametric chirp pulse amplification. I won't get into that. This is a picture of the gas being guided in one of these waveguides. And you notice that we have to be careful about solid plumbing design when we're putting these kind of pressures into this. And we do have to differentially pump. So what we do is we take a glass tube, we poke holes near the end, put gas in both ends, and then it leaks out the ends, and we just use some pumps to keep the pressure everywhere but in here very hot, very low. They're fine, actually. You have to know what you're doing with them, but when we use it with the Ti-Sapphire lasers for application experiments, you can have an accident where you hit it the wrong way, but otherwise they last forever. And actually, in this case with the mid-infrared lasers, the actual peak incident intensity that you need to generate higher energy X-rays is a little bit lower than it is in the former case. So I think everything should, these experiments were doable, and they didn't use dozens of capillaries. I think they might have fried a couple of them, but it worked just fine. This I added also for some of the experts in the audience, that another thing that we very clearly see in these experiments is in some cases we can see that the beam collapses. It undergoes a filamentary propagation where normally if you focus a laser into a gas and ionize it, since the index of refraction of the plasma is less than 1, the laser pulse tends to defocus. Under some conditions, people have seen filament propagation, which means that the pulse starts to focus and propagate in a self-focused geometry. And there's clearly some area of overlap between these high-energy X-ray generation and filamentary propagation. This is not exactly the same conditions as the 1.6 keV photons, but I think maybe if the wavelength of the laser is somewhat different, those conditions will coincide. The spectral bandwidth of this source is a broader coherent spectral bandwidth than any other light source that's ever been produced. Broad coherent spectrum means access to very short time scales by the Heisenberg time energy uncertainty limit. And in this case, there's the potential to use this spectrum to make a light pulse 2.5 attoseconds in duration. That time scale you can put in perspective when you realize that the physical extent of a 2.5 attosecond light pulse is about 7.5 angstroms, or the size of a small molecule. So it's a light pulse that's about the length of a molecule. I have no idea if that's useful for anything whatsoever, but it's a cool number. And this I think I'll skip. What? Our best guess is that these come out as chirped pulses with about a femtosecond duration. So you would have to compensate for the chirp to make a short light pulse. And but the thing I point out with that is that the experiments we're contemplating with a source like this, what you typically do is maybe you'd have a molecule and you'd want to see charge transfer from one side of the molecule to another. Well, you tag that molecule, there'd be a different element on one side or another, so you'd be looking at absorption edges, X-ray absorption edges of these molecules at various atoms at various locations within a molecule. If you wanted to look at attosecond timescale charge transport in that case, you don't need to make the pulse short. You just need to know what the chirp characteristic of the pulse is, and that is easily measurable. So it really does allow for new types of experiments on very, very short time scales, even without a heroic recompression of the pulse spectrum. That's a good question. We don't know at this point. They could be, and there is reason to believe that they may be, and that's simply because as we're engineering the phase matching of this process, phase matching is something that happens transiently. So the spacing between the individual bursts is getting larger, and the phase matching conditions changes more from cycle to cycle. So it's quite possible that this is a single burst, and we're setting up to try and measure that. Okay, I am definitely running out of time. I'll just mention that we have a company that is specializing in laser technology and is really trying to develop the laser sources that are needed for this work. This is just a little atomic physics. And the other thing I'll just briefly mention is that another part of our effort is in using these tabletop X-ray laser sources for applications. This is a good example application. Here what we did is we took coherent high harmonic light, and using a technique called coherent diffractive imaging, we were able to make images with an image resolution of about 20 nanometers using light at 13 nanometers. So near wavelength limited spatial resolution. And this is done, coherent imaging is an interesting technique where you illuminate an object with coherent light and you just look at this scattered light pattern, and from that pattern you can computationally extract out what the image looked like. It requires coherent light, and in this region of the spectrum you don't have good lenses or other optics. So this particular technique is ideally suited for this, and it gives a tabletop imaging capability that hasn't been possible in the past. We've also done some interesting work in magnetics. I know that I talked with a couple of you about magnetics in my appointments this afternoon, and I don't have time to talk about this, but I can after the lecture if you want. So I'll just finish up here. You know, hopefully I told you a compelling story here that this new physics of high harmonic generation gives us capabilities in laser science that we really thought were physically impossible, or physically impossible without an atom bomb, right? Which I think for most of us is the same thing. And we also don't know the physical limits of this process. 10 years ago, we thought we had found the limit. Now we don't know what the limit is. Can we make hard X-ray, coherent hard X-rays on a tabletop? Well, maybe yes. There are definitely technical challenges, but we don't know how far we can go. And we've, really sought to apply these light sources to a variety of areas in science and technology. So thank you, and thanks for your patience. Yeah. No, there's like no way you could get this target pressure in a jet. So, we take a hollow glass tube, we use a laser to drill holes at both ends, and then we put gas in those holes at high pressure. The region between the two holes should, at least in principle, be the same pressure that we're putting in. We know it's the same within a factor of 2 or so, but maybe not identically the same. And then a lot of the gas then just leaks out the two ends. Like that picture I showed you was 5 centimeters, so about this long. Oh, it's typically between 1 and 5 millijoules. There is not only one trick. And for example, we did a whole series of experiments where we did quasi-phase matching of the high harmonic generation process. That works great, But the complication is that all of the phase matching of this process is time dependent. And it's hard to think, that means that anything you do to fix phase matching has to also take into account this time dependence. We could do it in quasi-phase matching, but what we found was we could never make a jump of a factor of 10 because basically the coherence length so rapidly got so short that we couldn't do anything about it anymore. So this is definitely the simplest.
But this higher frequency data is from higher harmonic. But then the section that you are showing is other people who show in instantaneous.
Yes, it is a supercontinuous.
It's not about technology. It's about the physics. So the question is whether you'll get it low order nonlinear considered to the sensing low enough components to the self-measurement method. You don't just get it low order nonlinear considered to high order. Low would mean that the phase making ability is what
Is that a question? Should it be so?
whether it is possible to decouple.
Well, you're right, and there is a lot of work, for example, asking the question of whether maybe you're generating, how does the generation of low order harmonics affect the generation of the higher orders? The thing I can say is that, we've developed a fairly straightforward scaling here based on a simple physical picture, and it does a remarkably good job at predicting what we should see in the lab. This is, I think, really remarkable for this field because at some point people realized how complicated this high harmonic generation process is because of the time dependence of all of the phase matching conditions. Most people just gave up on trying to describe this. Even numerically, most people gave up on it, but the best people were doing was trying to do numeric simulations. Of course, numerical simulations don't give you a feeling for actually what parameters are important for scaling the process into a new physical regime. And that's what we were very happy to be successful with here, is that we really, after 10 years of thinking about this, we figured out, oh, this is how we can think about it. This is how we can describe it. Now we go into the lab, start making measurements. This worked better than we had any right to expect. So I think we have most of the physics there. Cascaded processes, they definitely do happen in high harmonic generation. But it's not clear how much of an impact they have.
So, you have mainly talked about phase matching, adding up the phases and so on. It's also important in high harmonic generation occurs at a limited space. So you have not commented on clusters or maybe solids, but if you get gas, you get close to these other properties.
Well, yeah, it's an interesting question. So one question we had was, at this very high pressure, is an electron going to be ionized from one atom and just bounce into a different atom and lose its coherence? In fact, if you do the basic calculation, you discover that there's 10 years ago when we were doing EUV high harmonic generation, every atom was completely isolated and you could calculate the excursion trajectory and it wasn't getting anywhere near any other atoms. This regime, the electron comes out, probably passes 1,000 neutral atoms in its trajectory to go back to its parent and recombine. It retains its coherence. The predicted optimum pressure that we predict matches pretty well with the experiment. And that kind of means that probably this effect isn't, that scattering off neutral atoms is not important. Now, that's not exactly what you're asking, but there's a whole lot of new physics there. Well, on a surface, then you're reflecting off it. Of course, we can't turn off the pressure forever because then we'd end up reflecting off the plasma, which would not be good. But
Do I understand correctly your picture that you have a continuous spectrum?
so the picture shows a continuous spectrum, but that doesn't tell us a whole lot because our spectrometer resolution is about 1 part in 500. And since the highest energy photons that we see are 5,000 photons coherently combined together, we don't have the resolution to see individual.
You mean that in reality it is a contrast?
We don't know. Actually, I answered that question before. I suspect it's a continuous spectrum.
If it is a continuous spectrum, what does it mean that you have a field?
It means that essentially it means that in principle we could compress this to the time bandwidth limit. That's what it is an interesting question because usually when we talk about coherent light, we're talking about monochromaticity. With short pulses, coherence just means deterministic phase relationship for all the colors of the light.
You can compress.
Yeah.
One of the biggest drives for developing coherent transformers is through crystallography of protein structure.
Yeah.
But it also requires monochromatic light. Do you think we can do this with your source?
I would love to be able to do this with the source. Do I think we can? I think it may be. Yeah, it's not going to be very soon, but it could be that in 10 years we'll start to see that kind of work with these sources. I've asked around quite a bit, and as far as I can tell, you need about 7 to 10 keV photons for crystallography. If you go to the scaling for this, what we need for that is something like a 10, I think about 15 micron drive light. Well, it's not going to be femtoseconds at this point because the optical cycles are getting longer than that. But it's going to be a pulse centered at around 15 micron wavelength would be necessary for that. We just don't know how to make femtosecond pulses in that wavelength range. I doubt it's impossible. I think that this work is now providing more impetus for technology development of femtosecond sources in the mid-infrared. And it will take some time, but from what we've done so far, the spectra that I showed we're taking with lasers running at 10 hertz repetition rate, which is enough to look at the spectrum, not enough to be useful. In the last year, we've developed lasers that are running at 10 kilohertz, and they're getting within an order of magnitude of the pulse energy that we need. So it all looks doable. But there hadn't been sufficient motivation in the past to make the lasers to drive it. And there's very little done on like nonlinear optical crystals that work at 15 micron wavelength. Well, there's some, but not a lot. So would going to relativistic intensity be good for this process? Yeah, so certainly for, there's a different type of high harmonic generation where you reflect light off a solid surface, and that you do at very, very high intensities. This process, actually, if you look at the scaling, the peak intensity you need is going down as your photon energy is going up. So you don't need the relativistic intensities. And in fact, probably one issue that we don't know about is it may be at some point that if your electron, so you have an atom here, you ionize an electron, it could be that the V cross B force causes the electron to miss the atom at some point, which will happen at relativistic intensity. So as far as I know, this process, no, you don't want relativistic. You want to avoid it, actually.
If your external field is so strong that the atomic field is not very strong in comparison to that, it goes very fast, then why simply free electrons cannot move the same bands?
Well, the free electrons are getting driven by this electric field. And that, in fact, is the origin of the index of refraction of the plasma that makes it actually possible to phase match. So, but to the extent that they collide with ions, they don't contribute to the coherent signal. So there has got to be some diffuse X-ray background going off in all directions, but it doesn't contribute to that beam. Yeah.